Hey everyone, welcome back to Tech Adventure. We will continue our journey into the field of embedded development skills. Today, we're diving into the fascinating world of real-time operating systems, commonly known as RTOS. In this video, we'll uncover the critical role that RTOS plays in the world of embedded systems. From its fundamental principles to its practical applications, we'll explore every aspect to gain a comprehensive understanding. Join us as we explore their crucial role in shaping the landscape of embedded systems. If you missed our previous video covering the essential skills required for embedded developers, I highly recommend checking it out first. We'll break down complex concepts into easy-to-understand bytes, covering everything starting from bare metal systems, basic introduction of RTOS to role, principles, features, and more. Get ready to learn and explore as we lay the foundation for your RTOS skills journey. Let's dive in. Before delving into the necessity of real-time operating systems, RTOS, in the embedded world, let's first differentiate between the two primary systems, bare metal and RTOS. By understanding their distinctions, we can appreciate why RTOS solutions are essential in certain contexts. In embedded systems, when operating without an RTOS, it's often referred to as bare metal programming or bare metal development. This means that the software runs directly on the hardware without the abstraction layer provided by an operating system like an RTOS. With RTOS, the software interacts with the hardware through the services provided by the real-time operating system. This allows for more structured and standardized development, with tasks managed by the RTOS scheduler and communication handled through RTOS mechanisms like message queues or semaphores. Let's explore the primary distinctions between bare metal and RTOS systems in embedded development. These differences shed light on why each system is employed in specific scenarios. Please pause your video and look once. Overall, the choice between bare metal and RTOS development depends on factors such as project requirements, development expertise, system complexity, and desired level of abstraction and standardization. Bare metal development offers greater control and flexibility but requires more effort, while RTOS development provides standardized mechanisms and simplifies system-level programming at the cost of some overhead. If you're enjoying the video, please consider giving it a thumbs up and subscribing to our channel. Don't forget to hit the notification bell to stay updated on all our future videos. We value your input, so feel free to share your suggestions for topics you'd like to see covered in the comments section below. When to use each? The decision to use bare metal or an RTOS in embedded system development depends on various factors. Here are some considerations for choosing between bare metal and RTOS. In summary, bare metal programming is preferred for simple, resource-constrained systems with deterministic timing requirements and low-level control needs. On the other hand, an RTOS is suitable for more complex embedded systems that require multitasking, task synchronization, portability, and scalability. Ultimately, the choice between bare metal and RTOS depends on the specific requirements and constraints of the embedded project. Now that we know why RTOS is crucial for embedded systems, let's explore its key features and fundamentals in more detail. Real-time operating systems, RTOS, are specialized software systems designed to manage tasks with precise timing requirements in embedded systems. Unlike general-purpose operating systems, RTOS prioritizes tasks based on their urgency, ensuring timely execution. Role of RTOS in embedded? RTOS plays a crucial role in embedded systems by providing deterministic behavior, multitasking support, and real-time task scheduling. It ensures that critical tasks are executed with precise timing, making it suitable for applications with stringent timing requirements. Example: in a robotic assembly line, the RTOS manages multiple tasks simultaneously, including motion control, sensor data processing, and communication with peripheral devices. The real-time scheduling capability of the RTOS ensures that each task is executed within its deadline, maintaining smooth and efficient operation of the assembly line. Principles of RTOS. RTOS follows certain principles. Here are a few important principles we can see. 1. Preemptive scheduling. RTOS uses preemptive scheduling algorithms to prioritize tasks based on their urgency and importance. Higher priority tasks preempt lower priority ones, ensuring that critical tasks are executed promptly. 2. Task synchronization. RTOS provides mechanisms for tasks to synchronize their execution and share resources safely. For example, semaphores and mutexes are used to coordinate access to shared data between tasks. 3. Memory management. RTOS manages memory resources efficiently, allocating and deallocating memory dynamically as tasks require it. Memory protection mechanisms may also be implemented to prevent unauthorized access to memory regions. For example, consider an embedded system controlling a robotic arm in a manufacturing plant. The RTOS uses preemptive scheduling to ensure that tasks related to arm movement, sensor data processing, and communication with the control panel are executed in the correct order and within the required timeframes. Task synchronization mechanisms prevent conflicts when multiple tasks access shared resources, such as motor control registers or sensor data buffers. Memory management ensures efficient allocation of memory for storing task data and program code, optimizing system performance and reliability. If you're enjoying the video, please consider giving it a thumbs up and subscribing to our channel. We value your input, so feel free to share your suggestions for topics you'd like to see covered in the comments section below. RTOS features and characteristics. 1. Low interrupt latency. RTOS minimizes interrupt latency, ensuring that time-critical tasks are not delayed by interrupt processing. This is essential for applications requiring rapid response to external events. 2. Configurability and scalability. RTOS can be configured to meet the specific requirements of different embedded systems, including memory constraints, performance objectives, and application domain. 3. Fault tolerance. Some RTOS implementations include features for fault tolerance and error handling, such as task watchdog timers and fault detection algorithms. These features enhance the reliability and robustness of embedded systems. Example: consider a medical infusion pump used for administering medication to patients. The RTOS ensures low interrupt latency to respond promptly to sensor inputs indicating changes in patient vital signs. The RTOS can be configured to handle different medication delivery protocols and dosage calculations, making it adaptable to various patient needs. Fault tolerance mechanisms detect and recover from errors such as sensor failures or communication errors, ensuring the safe and reliable operation of the infusion pump. Popular RTOS platforms. There are many RTOS available in the market, but here are some popular ones we can know. 1. RTOS, a popular open-source RTOS with a large user community and extensive documentation. It is widely used in IoT devices, industrial automation, and consumer electronics. 2. QNX, a commercial RTOS known for its reliability, real-time responsiveness, and scalability. It is commonly used in automotive infotainment systems, medical devices, and aerospace applications. 3. VxWorks, a real-time operating system developed by Wind River Systems, known for its performance, determinism, and support for mission-critical applications in industries such as aerospace, defense, and telecommunications. 4. ThreadX. ThreadX is a commercial RTOS developed by Express Logic, now acquired by Microsoft. It is known for its small footprint, fast context switching, and deterministic behavior. ThreadX offers features such as preemptive scheduling, inter-thread communication, event flags, and memory management. It is widely used in applications such as consumer electronics, automotive systems, and medical devices. Example: consider an IoT device used for environmental monitoring in smart buildings. The device may use FreeRTOS as its operating system, allowing it to perform tasks such as data acquisition, sensor fusion, and communication with a cloud-based server. The scalability of FreeRTOS enables the device to handle varying levels of data processing and communication requirements, making it suitable for deployment in different environments. To wrap up our discussion on real-time operating systems, RTOS, remember that RTOS plays a pivotal role in ensuring timely and efficient operation of embedded systems. By understanding its principles and features, you're equipped to navigate the complexities of real-time applications with confidence. Stay tuned for more insightful content, and don't forget to like, subscribe, and hit the notification bell to stay updated with our latest videos. Thanks for joining us on this embedded development skills journey. Until next time.